Thank you. Thank you. Hello, everybody. It's wonderful to be here. I want to start by asking a really fundamental question from the perspective of geologists, but I think from the perspective of all of us. Are humans so significant now as agents of global geological change that we rank with some of the great changes that have happened in the long history of our planet? So as a geologist, and as geologists, we use Earth processes that are acting at present to try and interpret what's happened over the long history of our planet. It's one of the great maxims of geology, and it dates back to the 18th century, but really it was crystallized by this man, James Hutton, in the early part of the 19th century. So we're using present processes to try and interpret the past. But also as geologists, we are very aware that the geological record can inform us about the degree of human-induced change at present. So what I want to do with you over the next 30 minutes is to look at the record of changes on planet Earth and ask the question, is the human impact as fundamental as some of the great changes of the past? Now you will have to bear with me because I have to start by trying to give you a sense of the sheer enormity of geological time. The planet that we live on is 4,500 million years old. And with a 30-minute talk, that means I've got to go at 150 million years a minute. So bear with me, hang on there, we're going to go quite fast. Earth is born 4,500 million years ago. It's bombarded with asteroids till 3,900 million years ago. Its oceans form about 3,800 million years ago. And then I think, from our perspective, the most momentous thing of all on this planet, life is born. Life on planet Earth extends back 3,800 million years. It's incredible. It's an unbroken chain of evolution from the earliest very simple organisms to all of the complexity that we see on planet Earth at present. And it's against this backdrop of the changes that we can see with the biosphere over 3,800 million years that we must measure the human change on planet Earth at present. Now, there are many people who still think that the human influence on planet Earth is not that great. And when I think of these ideas, I'm reminded of this wonderful lithograph from the middle part of the 19th century by the geologist Henry de la Beach. He was pillorying an idea of the time that evolution could recapitulate itself, that at some time in the future dinosaurs might reign again on planet Earth. Now, I don't believe that's the case, but I rather like this lithograph because you can see here that Professor Ichthyosaur is talking to his students, and they're looking at this rather feeble-looking organism preserved as a fossil. It's got very weak jaws, it doesn't look very strong. How could it possibly procure food? How could it be a dominant influence on planet Earth? But of course, nothing could be further from the truth, because we have fundamentally changed the hydrosphere, we have fundamentally changed the atmosphere, we fundamentally changed Earth's landscape, and we fundamentally changed Earth's biosphere. We are massive global agents of geological change. That's neatly summarized in this figure from a scientific paper published in 2008. It's looking at all of the different elements of the climate system on planet Earth that humans are potentially perturbing, that we're pushing towards tipping points where they may shift into a different state. And our influence is enormous. It extends from the polar regions with the potential damage that we can do to the polar ice sheets, to the tropics, to acidification of the ocean and the damage we might do to tropical reefs, or the way we might change long-term climate cycles in the Pacific, like the El Niño oscillation. So, if we accept that humans are global agents of change, what is the Anthropocene? What does it mean from my perspective as a geologist? So as geologists, to deal with the enormity of time, with a rock record that extends back 4,000 million years, we have to subdivide all that time. Otherwise, it simply becomes unfathomable. So this chart that you see in front of you has been unfolding for about 200 years. It divides up the rock succession, going from the very youngest rocks over there on the left to the very ancient rocks over there on the right. Now, you will know of this. You will know, for example, that the Mesozoic in the middle there is the bit that is characterized by dinosaurs. And we could potentially now think about adding a new interval of time to this evolving geological column. If we go right to the top of the left-hand column, we could potentially add an Anthropocene epoch of geological time, characterized by our actions. Now, these ideas aren't new. They extend back into the 18th and 19th century. Antonio Stoppani, Milanese geologist, was one of the first to use a term, Anthropozoic. He didn't use Anthropocene, but he was already recognizing that humans were global agents of change. And then fast forward a little more than 100 years to great Dutch scientist Paul Crutzen. He resurrects this term along with Eugene Sturmer. He uses it again, the Anthropocene time, Anthropocene era, to try and conceptualize the huge amount of change that humans have induced to planet Earth. And then a little bit later in 2008, my good friend Jan Zalazevich, who's a co-author of this talk with me, and myself and several others, published a research paper to suggest how we might go about constraining this Anthropocene epoch from a geological perspective. Let's think about the human signal. Our technology has left a fossil signal in the rock succession that extends back at least 2.5 million years. But of course, that technology is a shared technology because our great ape cousins also used technology. And so it's very deep, but we have a clear fossil record of the human impact on planet Earth. Or we could think about looking at the changes associated with agriculture, the domestication of cattle, the development of settled life about 14 to 13,000 years ago. That also has left a very distinctive signal in the geological record that we could recognize. We could think about our industrial impact that's been accelerating over the past 300 years. Again, it's left a whole series of artifacts around the planet that clearly are fossilizable and leave a signal of us. But think about the sheer intensity of change over the last 200 years. In the late 18th century, we could build an iron bridge that would span 60 meters. In the 21st century, we can now span 4,000 meters. It's an incredible change in a relatively short amount of time. We could think about the economic implications of what we do as humans. In the post-war period, post-Second World War period, we have the Great Acceleration, the time on planet Earth when we all have refrigerators, washing machines, tumble dryers, cars, the spread of McDonald's restaurants across the surface of the planet. It's exponential in this period, post-1945, and all of these have left a distinctive geological signal of you and me in the rock record. And this also coincides with the detonation of the first atomic bombs, and those atomic bombs produced from the fallout they generated a radiogenic signal. And we can see that radiogenic signal across the surface of the planet. It essentially defines an isochronous surface, a surface of equivalent time everywhere. And as geologists, we could use that potentially to define the base of our Anthropocene epoch. So we have all of these different competing ideas, and we haven't yet decided exactly where that boundary should be placed. So this is very much still an open discussion. Now, I want to focus on two aspects of the Anthropocene with you. Because of the time, I want to look at the biosphere and what humans have done to the biosphere. And then I want to briefly have a look at how we've changed the hydrosphere. And in particular, I'm going to focus in on rivers. The biosphere on planet Earth is, as far as we know, unique. And it is incredibly complex. It is a wonderful structure that has evolved over a very long period of time. It goes back 3,800 million years. It is resilient. It has undergone major extinctions. It has always bounced back and recovered. It's incredibly resilient. For 3,000 million years, it was relatively simple. It comprised essentially microbial life. You could think of this as a kind of bacteriosphere. And sometimes those bacteria might have formed colonies, but from our perspective, it's a very simple biosphere, not acting with all of the complexity that we have at present. And then about 650 million years ago, something momentous happens. Cells start to cooperate. They start to form the first bodies, sponges, the most basal of animal organisms. A little bit later, we see fossil evidence for the first animals, the first complex ecosystems on planet Earth. If we come forward a bit more in time, the geological record will show us another fundamental change. It shows us the evolution of organisms that have a head end and a tail end, a definite directionality to their movement, just like we do. And these animals make distinctive signals in the rock succession. So on the left there, you can see fossils from 540 million years ago of an animal moving through sediment. And on the right, you can see a modern animal making exactly the same kind of traces. It knows where it's going. It has a definite head end, and it's going for it. It's going in one direction. The first skeletons appear around about this time too. They're also probably associated with this directionality, because now things are hunting other things. And so you need to protect yourself. So you build a skeleton to protect yourself, but you also build structures to actually attack other organisms. Another momentous change. And this leads to all of the incredible complexity that we have in the ecosystems that we find at the surface of the Earth at present. For 540 million years, we have had complex, multi-tiered ecosystems on our planet. It's been a wonderful place for life. And then quite recently, only in the past couple of million years ago, we have the possibility of a geological imagination. With the evolution of sentience, with the evolution of humans, we can start to contemplate the changes that have happened on our planet. So all of these are fundamental and momentous changes in the evolution of the biosphere on planet Earth that we can measure our own potential impact against. So what then is unique about the biosphere that you live in at present? What makes the Anthropocene biosphere completely different from anything that has existed on planet Earth before? What have humans done? It's a fundamental question that we need to ask. Humans have definitely caused extinctions. We've been causing regional extinctions for 50,000 years. As we've invaded new regions, we can see the megafauna, the large mammals on the planet, disappearing. They're hunted by humans. They disappear. So we've certainly been agents of change for about 50,000 years in terms of what we've been doing to the biosphere. Many people, or some scientists, would suggest that extinction rates are now very high. This is very contentious, but nevertheless, we are certainly causing extinctions at the surface of the planet. And it's certainly true that species with small geographical ranges are increasing because of our curtailment of the biosphere. And it's those that are potentially the ones that will go extinct. So if we haven't caused an extinction yet, a big extinction event, we are heading in that direction. It's an important part of the Anthropocene biosphere, but it's not unique. It has happened before. In the last 600 million years, it's happened 6 times. There have been major extinctions on this planet. So although it's a significant component of what we are doing, or potentially doing, it's not entirely unique from a geological perspective. What is absolutely unique about what you and I have done to the biosphere on planet Earth? You might think, and if you Google this, you'll certainly find it on the internet, that humans are the top of the food chain, both on land and in the sea. That we sit at the top of the food chain as apex predators. But ecologists would not classify us in that way. Ecologists would look at what we eat, and we eat a whole range of different things, and they would put us at a mid-level in ecosystems. So we are not essentially at the top of these food chains. In fact, we're about the level of pigs on land. We're about the level of anchovy in the sea. So you are human anchovy from that perspective. That misses the point. It misses the point that we have displaced nearly all of the apex predators on the surface of planet Earth. And it also misses the point that we appropriate between 25 and 40% of all net primary production on planet Earth. That's incredible. For me as a geologist, I cannot think of a single time in Earth history when one species has dominated net primary production in that way. That is entirely unique. And to put it another way, 97% of the terrestrial vertebrate biomass is you and the things you have domesticated. Everything else is just 3%. That's incredible from a geological perspective. We've done the same in the oceans. We fish down the food chains. We fish out the things we really like, the apex predators, and when we fished all those stocks out, we work our way down the food chain. That's detrimental to those organisms that live in the water column, but it's detrimental to the seabed too, because those on the seabed are intimately linked with those in the water column. So we change the dynamics of the oceans also. We have transported organisms all around this planet. This is completely unique. There are now neobiotic species pretty much everywhere on planet Earth. Rabbits are a classic example, but of course you are the best example. You are a neobiotic species. You didn't originate in Holland or in Europe. You originated somewhere else. This has happened before. Organisms have changed their ranges in the past as a result of the continents moving around the surface of the planet through plate tectonics. So 3 million years ago, North America bumped into South America. And at this point, armadillos went from the south to the north, and many organisms from the north went to the south. And we can clearly see that in the fossil record. There's a clear fossil record of it. But what we have done is fundamentally different. We have altered the ranges of species across the entire surface of the planet. And we've also done it in areas that are geographically isolated, that could not possibly have these neobiotic species without the human influence. Even if you look at geographically isolated regions like New Zealand, I find this staggering. Number of native species, about 1,800. Number of neobiotic species, about 1,600. Nearly as many neobiotic species as indigenous species. So we've fundamentally reset the clock for ecosystem evolution. If we were to disappear tomorrow, we've fundamentally reset the geographical distribution of these organisms too, even if we were to disappear tomorrow. Entirely unique from a geological perspective. We've also fundamentally changed the landscape, such that it is very difficult now for you to find anywhere in Europe a landscape that's not been influenced by humans. This is wonderful work done by a gentleman called Earl Ellis at the University of Maryland in the States. And Earl has quantified the human impact over time at the surface of planet Earth. So I'm taking you back to 1700, or I'm taking you back with Earl's data to 1700, and you can see that even 300 years ago, the human impact is significant. Used landscapes are those totally dominated by humans, but you can see that humans already influence a whole range of what are styled semi-natural here. Let's go forward 300 years. Now, 75% of the ice-free landscape of planet Earth is dominated by humans. That is also fundamentally different from anything that's occurred in geological history. There's no example of this that I can think of from the fossil record where one species was so incredibly dominant in this way. Such that Earl would say the world is no longer dominated by natural ecosystems, with humans disturbing them, but rather is dominated by human systems with more or less modified natural ecosystems embedded with them. It really is an anthroposphere. And finally, one other thing that humans have fundamentally done to the biosphere is to interact with it technologically. And this interaction has been taking place over 2.5 million years, since our ancestors started to use technology and to change the landscape around them. It starts off very simply at first, but now, of course, in the 21st century, we are able to do incredible things from a technological perspective. Now we can take the photosynthetic pathways of prokaryotic organisms like cyanobacteria and potentially transplant them into so-called higher plants to improve their productivity, to make superplants so that we can feed more people in the future. This is a level of human-driven evolution. This is human-driven evolution. From superplants to not-so-super chickens. This is what we as a species have done to chickens over the past 50 years. I think it's a microcosm of everything that humans are doing on planet Earth. So we've doubled their biomass as individuals. There are 60 billion of them at the surface of the planet now, so it's literally the planet of the chickens. And it has left a fundamental geological signal, because these chickens are now architecturally different. They're anatomically different. And that will be recorded in the landfill sites where we deposit the bones of the chickens that we've been consuming. So a very, very distinctive geological and paleontological signal from my perspective also. I hope you'll agree with me that humans have fundamentally altered the biosphere. It is different from any prior state on planet Earth. I want to look at the hydrosphere with you also. And I want to do this particularly because we're here in Holland, the country which is the most famous in the world for engineering waterways. And so I think it's particularly good to do this. We could look at the oceans. They cover 2/3 of the surface of the planet, although they're only a very thin skin across the surface of our crust. But I want to focus in on river systems because they're very evocative of a landscape to us, and we've been connected to them as our civilization has been developed. So I'm going to show you what humans have done to river systems and how fundamental this is also from a geological perspective. But we could also go into the oceans and see similar human effects. Our influence is absolutely global. So I'm going to take you back into the geological past to a time 500 million years ago when there were no forests on the surface of the Earth, when there was no complex terrestrial biosphere. So you have to imagine a landscape, perhaps something like this, in which there are no trees, no shrubs, no grass. Maybe there is a thin veneer of a bacterial biosphere, maybe there are algae, but there's no complex biosphere. In such a world, rivers are completely different in their morphology. They run amok, they rampage across the surface because there is nothing to guide their pathway. And we can see this very distinctly in the geological record. If I take you back to rocks deposited 500 million years ago on land, and we look at the river systems, they'd look like this. They'd look like braided rivers running across the surface of the planet. And then something wonderful happens. A terrestrial biosphere starts to evolve, at first slowly, but then it gathers pace. And this happens from about 460 million years ago. So the forests, the plants, everything that you see outside of the terrestrial biosphere started to develop about 460 million years ago. It has a dramatic effect on the surface of the planet because, of course, the biosphere interacts very strongly with the landscape. Rivers are tamed. The morphology of rivers changes, and we see it in the geological record. Through this period, we see the evolution of river systems like these beautiful meandering rivers. The banks of these rivers are now constrained by the roots of trees and shrubs and plants that are holding those river banks together. So we see a fundamental change in the style of rivers where there is vegetation on the surface of the planet. And in tandem with that, we start to see the first animals invading the land. So this is an ancient river on the left, the rock deposits of that ancient river forming over 400 million years ago. And then you can see that there is this big tube coming down through the center of the sediments that have been deposited. That's a burrow system probably of a lungfish that lived on the land 400 million years ago. So now we've changed the whole style of the sedimentary rock succession on the land as a result of this terrestrial biosphere. Why is it relevant to look at this? It's relevant because humans are now changing this river landscape. We are doing human reverse engineering to parts of the hydrosphere, to river systems. We've significantly altered the flux of sediments running down rivers. We deforest areas, we use agriculture, we mine areas, we build transportation systems, all of which change the path, the track, the morphology of rivers. In fact, now there's something like 200 cubic kilometers of sediment that's human-induced going down rivers every year, which has also, of course, affected the way that sediments are accumulating on the continental shelves around our continents too. We've been generating new styles of rivers since classical times. You could look at the river Tiber, exiting into the Mediterranean Sea, the port of Ostia, And if you look at the succession of sediments that were forming at the time that the harbours were being built here in the 1st and 2nd century AD, it's fundamentally different from the natural sedimentary succession that was accumulating there. Humans, since classical times, have become global agents of river change. We leave a distinctive mineralogical signal in our rivers also from all of the different human products that we produce, and this is preservable long term. So this would leave a distinctive geological signal in the rock succession also. Think of the river which is most evocative of classical times, of the development of the cradle of human civilization. Take the Nile, for example, and then think of what humans have done with the Nile. We've fundamentally altered it. If you look at all the structures associated with the Nile, it is dammed. There are reservoirs. It's used for irrigation. All of those structures are potentially fossilizable as a signature of human-produced burrows, if you like, associated with that river. But also, the agricultural signal would leave a distinctive fossil signal from the products of that agriculture. So a fundamentally changed system. This system's been accelerating. We build barriers and dams. We build our own rivers. Holland is the best place on planet Earth to illustrate that. We use water to deal with our waste. We build huge structures next to rivers called megacities. And those megacities are potential huge fossils of the future with the materials that they produce both above ground, but also with the very, very extensive structures that they produce below ground. Again, all potentially fossilizable as a signal of what humans have done at the surface of the planet. Think about London, developing over 2,000 years. In the middle of the 19th century, it becomes the world's first megacity. It cannot cope with the number of people influxing into the city. Its transport system is collapsing. It cannot move people around the city. What does it decide to do? It starts to form a new kind of borough system, something which is a distinctive signal of humans. Remember our burrows from long ago with animals that had directionality? Remember the first burrows that we find in the geological record on land about 400 million years ago? Now you have a new kind of burrow system being formed, but this one is distinctly human, and it is indicative of the sheer capacity of humans to change the landscape and below the landscape. So in 1861, the world's first metro system starts to be built in London. By 1907, it is a gigantic trace fossil below the ground that will be preserved into the future. And of course, this technology then spreads throughout the world and is a global signal of the impact of humans wherever we find large cities on planet Earth. Think about the complexity of these structures. This is just one metro station in London. This is Piccadilly Station. It is enormous. It is enormously complex. Much more complex than anything that we see in the geological record produced by any component of the biosphere in the past. It is a wonderful signal of our ability to modify and change the landscape. Wonderful, perhaps, with inverted commas. It is a symbol of where we are now at in the 21st century with our global interconnectedness, with our ability to move more sediment than all of the rivers by themselves. Humans are such enormous agents of global change. It's where we're at. We are globally interconnected. Our behavior has changed. And a signal of that behavioral change in the biosphere, as we saw in the past, is our capacity to build these huge underground structures. Now, we could argue that all of these changes are transient, that if some catastrophe occurred tomorrow and all humans disappeared from the surface of the planet, that the biosphere would recover to some kind of equilibrium state. Even if we disappear tomorrow, from a geological perspective, the changes that we have produced in the biosphere, in the hydrosphere, in the structures that we have generated are so significant that we have left a signature of us far into the future. And so if Jan's space aliens were to visit this planet in 1 million years' time or 500 million years' time, they would see evidence for us. and we would have defined our interval of time, the Anthropocene. At least that's my perspective. But I want to leave you with one thought. This process shows no sign of slowing. If it is accelerating, if in fact this will continue into the future, then we are at the beginning of a fundamental state change on planet Earth, that we are changing the biosphere and the surface of the planet forever, and that our change, our induced change, ranks in significance with some of the most fundamental changes that have occurred to the biosphere in the deep geological past. Thank you very much.